Dear students, today we will be discussing about the different components, applications and design of off-grid solar PV systems. So, these are the content of our discussion today. First, we will start with application, then different components which comprise of a off-grid solar PV system, then design approach. So, what are the applications of off-grid solar PV systems? So, it may be water pumping, maybe street lighting, medical refrigerator, telecommunications and signaling, remote refrigerator, and there are many more applications of off-grid solar PV systems. Of course, we have to mention like household applications, because mostly we can use it in many of the utilities applied in household. So, as far as component of a off-grid solar PV system is concerned, as you can see, it comprises of PV modules of required number, charge controller which protects the battery for overcharging. We will have inverter. If our load is AC load, then we have to convert DC current to AC current, but if we have DC load, then there is no point of installing an inverter, right. So, the kind of energy output we will get, it is DC, right. So, we can convert it by using an inverter, and we have sufficient number of storage to meet the load during off peak hours. So, in nutshell, this system comprises of PV modules, mounting structures, charge controller, battery, inverter or DC-DC converter and cables. So, all the components are essential, and we need to consider the efficiencies of all the components while designing a such kind of power plant. And also we can see the applications of off-grid solar PV in irrigation. So, here we have PV modules of required number which can be used for lifting water, and we have to provide this energy to the motor. It may be DC or AC. If it is AC motor, then we need to install an inverter, and then this will lift water from the ground to the reservoir, and from here we can distribute the water in the irrigation field. So, in this system there is no battery backup unit. Another example is use of off-grid solar PV systems in street light. So, we have PV modules of required number based on the requirement of the load. We have to specify the number of modules. Then we will have charge controller. Then if it is DC load, then we can provide the energy directly to the DC load, and if AC load is present, we need to install an inverter to convert DC current to the AC current, and we can charge the batteries when we are not utilizing the energy for providing to the loads, and this stored energy can be used at nights, right. For street lighting system, normally we need the energy at night. So, our primary intention is to store the energy in the batteries during the daytime when sun is available, and stored energy will be utilized at night time. Okay. Also, we can think of this kind of technology. Other components are same. Here only backup is generator in order to provide uninterrupted power supply, right. So, generator provide energy, and then it goes to inverter, then we can provide loads. Okay. So, other components are same as what I have discussed in the last slide. So, we need to understand the component very precisely about solar PV, how to design, how many numbers of modules are required to meet the demand, how many batteries are required, and how these configurations to be made What I mean, like number of batteries to be connected in series or number of batteries to be connected in parallel, number of modules to be connected in series, number of modules to be connected in parallel, all those things need to be considered, and along with that we need to consider the cable length, because it has also got inefficiencies. So, we need to consider all the components when we talked about a design system. So, let us first discuss some of the battery parameters, because battery plays a vital role in investigating the performance of a off-grid PV system. So, one of the parameters is C rate. How it defines and what it measures? C rate measure rate of discharge of battery relative to its capacity. A brand new battery with 10 ampere hour capacity theoretically can deliver 1 ampere current for 10 hours at room temperature. Okay? That way we can do for other batteries as well, having different capacities. Also, we need to know the different efficiencies used for investigation of a battery. What are different efficiencies? We have voltaic efficiency, coulombic efficiency, and finally combination of both. Like when we multiply volumetric efficiency and coulombic efficiency, what we will get is battery efficiency. So, how do we define volumetric efficiency? Is the average discharge to the average charging voltage. Okay. For coulombic efficiency, how do we define? Is the ratio of total charge got out of the battery to the total charge put into the battery over a full charge cycle. And as I said before, this battery efficiency is combination of volumetric, voltaic and coulombic efficiency. Okay. So, mathematically it can be represented by V discharge to the V charge multiplied by Q discharge to the Q charge into 100%. Right. Few more parameters we need to learn, like state of the charge. How do we define state of the charge? It is defined as the percentage of the battery capacity available for discharge. So, mathematically we can write SOC is equal to E bat, which is the battery capacity, and this is the energy of the battery, and C bat is the battery capacity and V is the voltage. So, here a 10 ampere hour rated battery that has been drained by 2 ampere hour is said to have a SOC of 80%. That is how we define SOC. Also, we need to learn what is depth of discharge. It is defined as the percentage of the battery capacity that has been discharged. In short, it is called as DOD, which is equal to C bat multiplied by voltage minus E bat to C bat multiplied by voltage. So, for your understanding, we can visualize in this way: a 10 ampere hour battery that has been drained by 2 ampere hour has a DOD of 20%. Okay. So, this SOC and DOD are complementary to each other, as you can see now. Also, we need to know what is cycle lifetime. So, it is defined as the number of charging and discharging cycle after the battery capacity drops below 80% of the nominal value, right. The colder operating temperatures means longer cycle lifetime, and the smaller the DOD, the higher the cycle lifetime. These points need to be remember. Also, voltage, the nominal voltage at which the battery is supposed to operate is very important. For solar batteries, these lead acid grid plate batteries are usually rated at 12 volt, 24 volt or 48 volt. Again, we need to define capacity, the amount of charge that the battery can deliver at the rated voltage, which is known as the capacity. The capacity is directly proportional to the amount of electrode material in the battery. That means, higher the battery size, higher will be the capacity of the battery. The voltage of the cell is more chemistry based, while the capacity is more based on the quantity of the active material used. So, that is how this voltage and capacities are different. Okay. This voltage is mostly dependent on the chemistry of the battery, but the capacity is depends on the mass of the batteries. The capacity is measured in ampere hour and charge usually measured in coulomb. As the electric current is defined as the rate of flow of electric charge, ampere hour is another unit of charge. Since 1 coulomb is 1 ampere second, that means 1 ampere hour is 3600 coulombs. Okay. And when we are talking about energy capacity, the energy capacity of the battery is defined as E bat, which is nothing but C bat into the voltage. Okay. And this will be in watt hour. So, we must know what is the capacity of the battery and then voltage. Okay. Then what we can find out is the energy capacity of the battery. Fine. So, with this background, we can now move forward for design of the PV system. So, design principle, when we are talking about, then we need to concern many of the things and we need to follow some appropriate steps while designing the off-grid PV system. So, a major component of off-grid system is the storage component, which can store energy in time when PV system generate more energy than required, and it can deliver energy when the electricity generated by the PV module is not sufficient. Okay. Also, we need to know like how many days autonomy is required. Autonomy means, suppose if the weather condition is not good for a particular place, say for 3 days. So, we need to maintain the load or we need to deliver the energy from the solar PV. Then under that condition, we need to keep backup for 3 days. So, that is how we define the autonomy of the system is 3 days. So, that means the number of days a fully charged storage must be able to deliver energy to the system until discharged. When we are talking about sizing of PV arrays, we need to talk about both PV arrays and storage system. These two are interconnected. There are two situations arises. First is E fail, that means the energy required by the electric load that cannot be delivered by the PV system. What is the situation? If the batteries are emptied after several cloudy days. And second condition is or situation is E dump, that means the energy produced by the PV array that neither is used for driving a load nor is stored in the battery. What is the situation? If the batteries are already full after a number of sunny days. So, these two are the very critical situations we need to look into. Now, we need to size based on the reliability of supply. The reliability of electricity supply is an important factor in the PV system design. One way to quantify reliability of supply is by loss of load probability, in short LLP parameter, which is defined as the ratio of the estimated energy deficit to the energy demand over the total operation time of the installation. So, mathematically it can be represented by LLP is equal to E fail integration of PL T dt, okay, E fail to the integration of PL T dt, right, and this is for yearly basis. Why? Because load profile is varying. So, because of that we need to find out this EL this way. We need to integrate over the period of 1 year, right, and this will be in watt hour or kilowatt hour per year. So, lower the LLP, more stable and reliable the PV system would be. So, our intention is to keep the LLP value at the lower condition. Okay. So, we can dig it more. So, this PV array capacity and storage capacity, two very important parameters which are defined something like, when we are talking about PV array capacity, which is nothing but the ratio between the mean PV array energy production to the mean load energy demand, and storage capacity, which is represented by CS, is defined as the maximum energy that can be taken out from the battery to the mean load energy demand. We can estimate the values of CA and CS by using this expression coined by Aguido and Lorenzo. So, these are the two expressions we can use for calculation of PV array capacity and storage capacity, where eta PV is nothing but PV array efficiency, A is the PV array area, and HT is the mean daily irradiation on the PV array. It should be in watt hour per meter square, and L is the mean daily energy consumption in watt hour, and C is the useful accumulator or battery capacity. You can write battery as well, which is represented in watt hour. Also, if we are interested about long term average of daily irradiance, then our expression will send something like this: CA dash is equal to, this is for PV array capacity, A HT bar to L, right. And what is HT bar? HT bar is the monthly average daily irradiation on the PV array, and its unit is watt hour per meter square, right. Now, the reliability of a PV system is defined as the percentage of load satisfied by the PV system, right, but LLP is reverse, which is defined as the percentage of mean load not supplied by the PV system. Okay. So, that is how these two are different. Now, let us pay attention about this plot and its important observations. So, this plot shows about the relationship between PV array capacity, storage capacity and PV system cost. We have different conditions at different points, and this CA and CS plan represents a size of a PV plant. So, if we consider any point, so this represents the size of a PV system, and this curve, solid curve, is the loci of all the points corresponding to the same LLP values. Okay. So, this is maintained at an LLP of 0.01. Okay. So, here we can make some of the points. Larger the PV system, the greater is the cost and lower the LLP value. So, that means we have to increase the cost, but our target is to minimize the cost. Okay. At the same time, we need to minimize the LLP value. So, the task of sizing PV system consists of finding the better trade off between the cost and reliability. And always there is a problem to find the CA and CS values that leads to a given LLP value at the minimum cost. Okay. So, this is the curve we have generated, and we can see different points here. Say 2 is the CS value, and correspondingly you can say close to 1. That means what? At this condition, the proposed reliability is achieved by having a big generator and a small storage capacity, right? And at this condition, so storage is 9 and here PV array is 0.6. We have small PV array here and big battery here, okay? That also increases the cost. But if we consider this point, so we will have CS value of 7.5 and this is about 0.62. Under this condition at LLP value of 0.01, this is found to be the optimum size, because it minimizes the cost of PV system, right. This is the minimum cost of the PV system. That is how we can optimize the system, right. And there are recommended values of LLP, like for domestic applications its value is about 0.1, rural home lighting 10 to the power of -2, and telecommunications it is 10 to the power of -4. This is already recommended, right. Now, let us move to the derivation part. So, this is nothing but the PV topology of an off-grid system. We will have PV systems, then MPPT here, maximum power point tracking. This is charge controller, this discharge controller, we have inverter, then load, right. And in between we will have battery bank. So, solar radiation falls here and then it goes through MPPT and then charge controller, and then we have storage if we need to meet the demand at night or off peak hours, then we have to store and we can use it. And again, if we have DC load, then directly you can go to the load, and if you have AC load, then this has to pass through inverter, right. Sometimes these MPPTs are not installed, but it is assumed that here MPPT is installed and these components are actually not staged together always. So, now if we talk about the purpose of this charge controller is to prevent the battery bank from being overcharged by the PV system. And what is the purpose of discharge controller? It prevents the battery to the discharge below the minimum allowed state of the charge. That means, both the CC and DC controls the life of the batteries, right. And now we will discuss the derivation of voltage of the batteries as function of PV system parameters. Then we will go for energy balance to solve the or design the off-grid solar PV system. Now, let us discuss about the battery bank. The battery bank is the workhorse of any off-grid system because it is a stable power source. It is thus very important to understand how the battery bank will act in the PV system. So, we can have this IV characteristics or IV curve of an idealized battery bank, IV curve of an idealized battery bank. So, I will draw here, I do not need this. So, if we say VOC is here and we will have VBB surging and VOC battery bank, and we will have this VBB discharge. So, we can plot it something like this. This is IBB surging, and we will have IBB discharging, okay. And this part is surging and this is discharging. And this represents current, this is voltage, right. So, to know how a battery works, the net effect of all the forces that try to charge or discharge the battery need to be understood clearly, okay. And this VOC BB will not be constant, but a function of the state of charge, ambient temperature and other parameters. So, mathematically what we can write as VOC BB is a function of SOC, then ambient temperature, I will represent TA and other parameters. This may be equation number 1. But in our analysis, variation of VOC with respect to this SOC, TA and other parameters are neglected. Okay. Now, let us write down the expression for IBB, which is RI VBB minus VOC BB. This is because this RI is the resistance, because I can draw this figure as well. So, this is like RI and voltage drop is VBB minus plus, so minus plus POC PB. Because of this RI what is present here, this VB will be different than VOC BB, okay. And also it depends on the current IBB flowing through the battery. So, I can write this as equation number 1, and if we consider the power on the left side and right side of MPPT, you can go back. This is the MPPT part. So, we are interested about left side and right side of the MPPT power. Then what will happen here? We can write So, if we represent the efficiency of MPPT is MPPT or MPP you can write. This is something like ICC IBB to IMPP multiplied by VMPP. Okay. So, again you can simplify this expression ICC IBB is equal to eta MPP IMPP and VMPP. Okay. And we can assume a value which is, or the parameter called beta. Okay. So, this may be equation 3 and we can write ICC in terms of beta. So, eta MPP IMPP VMPP to IBB. Okay. So, this is something like beta by I, this is V, this is V, this is V, and of course, this will be V and this is M. Okay. This will be V B B, right. This is equation number 4. So, here this parameter beta, this if beta is 0, what does it mean? That means this PV system is not active, maybe during night. So, during night beta will be 0, right. So, we can also now study the cases where power on the left and right hand side of the inverter. So, if we consider I inverter is the inverter efficiency, then we can write something like I inverter is IAC to VAC, this is AC power output to the I inverter input and VBB. Okay. So, this maybe we can visualize something like IAC, then VAC is equal to eta inverter multiplied by I inverter then VBB. So, if we consider this part and we define a parameter alpha, so it will be alpha times inverter. Okay. So, here if we are interested about inverter current, then this will be something like IAC, VAC, then I inverter, then VBB. Then if we substitute the expression what we have written here, so it will be something like alpha tau infinity, alpha multiplied by efficiency of the inverter, then efficiency of the inverter multiplied by VBB. So, this term goes off, then it will be alpha by VBB. Okay. This may be equation number 5. Okay. Now, if we combine earlier expression, like we know I BB is 1 by RI VBB minus VOC BB, and IBB is equal to ICC minus I inverter, then it will be beta minus alpha VBB. So, these two expressions we can use for further derivation, and here if we see in this expression, so what will happen if alpha is 0, and what does it mean? It indicates no load is present, right. Now, if we use those expression, and what we can get at the end is like beta minus alpha divided by VBB is equal to 1 by RI VBB minus VOC BB. Okay. So, this equation is 6 and this is 7, right. So, now if we multiply this equation 7 by RI into VB BB, then what we will have, this equation 7 reduces to RI beta minus alpha, okay. This BB goes off, then here RI will goes off, then what we will have is VBB square minus VBB multiplied by VOC BB. Okay. So, if we rearrange it, is something like VBB square minus VOC BB VBB, then the minus RI beta minus alpha is equal to 0. So, this is nothing but a quadratic equation. Okay. So, what are the solutions of this equation? Solutions will be something like VBB plus minus is equal to minus B means OC BB divided by 2 plus minus root over VOC BB minus 4 is 1, this is 1 and C is, this is minus, right, minus okay. So, we can simplify it something like VOC BB divided by 2 plus minus square root VOC BB divided by 2 whole square plus RI beta minus alpha. Okay. Fine. So, this is equation number 9, right. So, positive solution, because in negative solution what will happen, this will be 0. So, positive solution will be VBB VOC BB plus VOC BB divided by 2, which is nothing but VOC BB, right. Okay. So, this may be equation number 10, fine. So, this is the positive solution. Otherwise, if we use this negative sign here, or the other solution VBB negative will be VOC BB divided by 2 minus VOC BB divided by 2, it will be 0, considering beta minus alpha is 0. Okay. So, the final solution would be VBB is equal to VOC BB divided by 2 plus square root of VOC BB divided by 2 plus R I beta minus alpha. Okay. So, this may be equation number 11. Now, let us discuss about the surging and discharging phenomenon. So, for surging, if the battery is charged, then ICC is higher than the current to the inverter, and hence beta minus alpha and IBB are positive. Okay. And BB is higher than VOC BB during surging. And in case of discharging, what happens? If the battery is discharged, then CC is lower than current to the inverter, and hence beta minus alpha and IBB, that is battery current, are negative, and BB will be lower than VOC BB, right. The net current IBB is equal to ICC, that is battery bank current and surging current are same, which flows in and out of the battery. Therefore, only this current determines the power loss in the battery. Okay. That is how we can write this expression, PBB loss is IBB square into resistance. Okay. And this power is always lost irrespective of the sign of IBB. And there are some recommended number of autonomous date at several latitude. So, for 0 to 30, DA value is 5 to 6, and 20 to 50 it is 10 to 12, and 50 to 60 latitude recommended days of autonomy is about 15. Now, let us design an off-grid system with energy balance. The analysis for load side and PV side is performed separately in this process. So, how it is done? Let us begin with the load side. So, first we will determine the annual load, how much load is required annually. So, this can be mathematically represented by ELY is equal to integration of PLT dt, and this time is for 1 year. And if we are interested for daily, then that can also be done like by dividing this ELY by 365, right. So, the amount of energy which is required from the battery side we can calculate by using this expression EBB, this required energy of the battery bank is equal to dA multiplied by EL to the power of D multiplied by SF battery and then DOD max. So, what is DA? DA is the autonomy. How many days we need to keep the autonomy? If solar radiation is not there, then we need to keep the energy in certain devices like in batteries. For how many days we can keep it? So, DA is actually responsible for that. So, this an adequate number of days of autonomy need to be selected depending upon the location and a basic understanding of weather pattern. So, this is very important. And what is SF? That is surging factor. This is about 1.1 times we need to consider, and DOD max is the maximal allowed depth of discharge of the batteries. And also we need this information that the rated energy of the chosen batteries. So, this is for the battery bank, the entire batteries. It may be 6 batteries, 7 batteries, 8 batteries, 12 batteries. So, altogether we name it as battery bank, but here what we are concerned about single batteries. Okay. So, this energy which is nothing but rated energy is equal to VOC, open circuit voltage of the battery, multiplied by battery capacity. So, this battery capacity is represented by ampere hour. So, once we know this EBB, that is energy required of the battery bank and rated energy, then we can calculate the required number of batteries by using these two expression EBB to the EBAT. Okay. This is the battery bank energy and this is the rated energy of a single battery. So, we can calculate the number of batteries, right. So, once we are done with that, then we can go for inverter selection. So, two important factors we need to concern. One is consider the maximal load power, and it may be more beneficial to choose a system design such that not all the appliances can be used at the same time. Okay. So, this is one concern. Say for example, we need to consider some of the natural convention. Say during evening time we should not use irons, only we need lights. Okay. Maybe washing machine we can schedule it, maybe the daytime we can do it. Okay. So, that way we can suggest some better design, but of course, sometimes it might so happen that we have to connect all the load at a time. So, we must know the total amount of load and accordingly we need to design the system. So, here in this case we have 3 requirements that need to be seen. First is the maximally allowed power output must exceed the maximal power required by the appliance. So, mathematically we can write it something like P DC inverter is max greater than PL max, this is for load, right. And second concern is the nominal power of the inverter should be approximately equal to the maximal load power. So, mathematically we can write PDC is equivalent to PL max. And third concern is the nominal inverter input voltage should be approximately equal to the nominal voltage of the battery bank. So, mathematically we can write something like this, VDC inverter equivalent to BOC battery bank. So, these 3 concerns we need to keep in mind while designing an off-grid solar PV system in general and inverter in particular. So, now let us see the adjustment of the batteries. Typically, this voltage for the battery banks are 12 volt, 24 volt, 48 volt, 96 volt. Say for example, if we consider a battery bank of 48 volt and single battery provides 12 volt, then we can calculate how many batteries are required to be connected in series, right. It will be 4 batteries to be connected in series. That way we can have some kind of understanding, but basic voltage normally considered is 12 volt, then we multiply by 2, then 3. So, if we are interested to connect the batteries in series, then how we can do the calculation? If we know the open circuit voltage of the battery bank and open circuit voltage of a single battery, then we can find out like how many batteries to be connected in series. That means, if the battery bank voltage is 48 as I said before and single battery voltage is 12, then it will be 4. So, 4 batteries are to be connected in series, right. Then how to connect the batteries in parallel? Then what are the parameters you need for this? So, we need this number of batteries and then number of batteries which are connected in series. Then we can find out the number of batteries to be connected in parallel, right. So, these informations are also required while designing the PV system. And now, let us consider the case towards PV side of the system. So, energy balance can be written as this DC output of the array is equal to this load output, that is load per year multiplied by sizing factor. As I said, this sizing factor is usually assumed to be 1.1. Okay. That means, that is energy at the DC side is about 1.1 times the load side, right. So, if we need to find out the number of modules required, then we can use this expression, this EDC yearly, which is equal to ELO yearly multiplied by sizing factor divided by amount of solar radiation which is falling in a year multiplied by the area of a module, right. So, once we know this number of modules, then our next step is to find out like how many modules are to be connected in series and how many modules are to be connected in parallel. And one thing we need to remember, like for minimizing losses, the maximum power point voltage of the PV array and the nominal voltages of the inverter and the battery pack should be approximately equal. This is one of the important aspect we need to remember. Now, we are concerned about series connection of the PV modules in that array. So, once we know open circuit voltage of the battery bank and then average voltage of module MPPT, then we can find out the number of modules to be connected in series. So, this V mod MPP denotes the annual average of MPP voltage of the PV module. Of course, maximally allowed input voltage of the MPPCC unit must not be exceeded by the PV array. So, that is how we can write mathematically V MPP, this voltage at maximum power point greater than or equal to NS, that is number of modules to be connected in series multiplied by V max mod MPP. Okay. So, next we can do the parallel connection of PV strings. So, it will be something like number of modules to the number of modules connected in series. So, once we do this, then we can find out what is NP, right. So, this way we can find out the number of modules to be connected in series, number of modules to be connected in parallel. So, these all are design components, right. So, in summary, what we have done in this lecture, we have studied different components which comprises of a off-grid solar PV system, its applications and its design procedure. I hope you have enjoyed this video. So, in the next class, we will be discussing about a numerical problem to strengthen your understanding. Thank you.